Alright, the next chapter deals with chemical equilibrium, which is similar to what we just talked about at the end of the last chapter with that reaction mechanism. This is an important concept because we're going to be using this for the next several chapters. Okay, so you need to get an understanding of this in this chapter because we will be using the same groundwork to do other future chapters. Previously, we've assumed that chemical reactions result in the complete conversion of reactants to products. In Gen Chem 1, you did reactions, and basically you assumed that all A and B was consumed up and we formed C's and D's. Then you might have had a limiting reagent problem where only one of the components was consumed, but the reaction still stopped because you didn't have any of that component. So reaction came to a halt. Many chemical reactions do not completely convert reactants to products. They stop somewhere in between no reaction and complete reaction. So what you have is some A and B left, as well as some C and D being formed. You have a little bit of everything, okay? Nothing's been totally consumed. So we have some A, some B, some C, and D. What happens in that case is we end up writing a double arrow, basically saying that we have the reaction going in both directions. I have A and B forming C and D, but I also have C and D forming A and B. And what we get is a state of called equilibrium. So I have A and B forming C and D. When I reach this point of equilibrium, I have C and D forming A and B, but it's doing so at the same rate. So basically A and B is forming C and D at some forward rate, and I have C and D forming A and B at some reverse rate, and those rates are equal. When I'm at that point of the rates being equal, I have what we refer to as an equilibrium condition. Okay? The reaction is still going on, it's just an exchange going on. Okay? As fast as A and B is being consumed, C and D is producing it again. So what you end up with is a constant concentration of the different species. Each species having whatever concentration it has, but it's becoming some constant value when I reach equilibrium. As fast as I consume it, the other reaction is producing it. Therefore, many reactions do not go to completion, but rather form a mixture of products and unreacted reactants in what we refer to as a dynamic equilibrium. Dynamic equilibrium consists of a forward reaction in which the substances react to get products and a reverse reaction in which the products react to give the original reactants. In other words, an exchange going on. Chemical equilibrium is the state reached by a reaction mixture when the rates of the forward reaction and the reverse reactions have become equal. In other words, my forward rate is equal to my rate of my reverse. They become equal when we reach that point of equilibrium. Now we can show this graphically. Okay. Say I have a reaction of A plus B gives me C plus D. I can write a graph, but basically I have my concentration on my y-axis and time on my x-axis. If I have the reaction of A and B, I have some concentration of A, and I have some concentration of B. Okay. Over time, these molecules will be colliding, and the concentration of A and the concentration of B will be going down over time. They will be getting less over time. At that point where the concentration of A and B are getting less, my forward rate will also be decreasing over time because the probability of collisions go down. At the same time, I'm producing C and D, so I have concentration of C and concentration of D. Those concentrations are going up over time because I'm producing them. So it has some reverse rate, okay? Well, as the concentration of those are increasing over time, okay, eventually concentrations will level out just like they did with the A and B, and your reverse rate will be increasing over time. At some point, the forward rate and the reverse rate will be equal. That's going to occur when my concentrations of A and B and C and D reach some constant value, some constant concentration. My A and B also will reach some constant concentration. That point where that occurs Okay, that's my equilibrium. That's the point that my forward rate will be equal to my reverse rate. So that point where the concentrations become constant of A, B, C, and D is that point of equilibrium where my forward rate will be equal to my reverse rate. Since these rates are equal, there must be some mathematical relationship to show that, and we'll show you that in the next couple of slides. But first I want to show you a slide of a real example of this graph using a reaction. Here I have 3 moles of H2 plus 1 mole of carbon monoxide gives me 1 mole of methane plus 1 mole of water. Notice that if I start off with my moles of substance, I'm starting off with 3 moles of hydrogen moles of gas, and you can see that it basically decreases over time and then it levels off. Okay, start off with 1 mole of CO. Once again, it levels off at some point. And then we're producing methane and water moles, both being 1 mole each, so that's increasing over time, and then it levels off. We can look at the rates. The forward rate of this reaction is decreasing over time. Okay, so 3 moles of H2 plus 1 mole of CO over time, that rate will decrease. Well, on the other side, I have methane and water producing H2 and CO. Since this is a reverse reaction, this rate is increasing over time until that rate levels off. That point where my forward rate and my reverse rate equals, okay, that will occur at the same point in time where my concentrations level off. So when my concentrations level off to some constant value, that is the same point that my rates will be equal, and is what we refer to as equilibrium. That is that point where we reach equilibrium. So mathematically, there must be a way to relate this. So what we're going to do is assume these reactions to be elementary reactions. So let's look at the forward reaction. So I can say if I look at A plus B gives me C plus D, I can write the rate law directly for this since it's an elementary reaction, which would be my rate forward equals to Kf times the concentration of A to the first, B to the first. I can now look at the reverse reaction. C plus D gives me A plus B. And I can write that one as my rate of my reverse equal to Kr, my constant for the reverse, C to the first, D to the first. Okay, can read those directly because we said they're elementary reactions. By definition, we said at equilibrium, the forward rate equals the reverse rate, which means then that my two expressions must be equal as well. So then I have Kf, concentration of A to the first, B to the first, equal to Kr, C to the first, D to the first. Now what I want to do is get my constants together on one side and concentrations on one side. So I'll bring down my Kr and take my AB and bring it over to the other side, which rearranging gives me Kf over Kr equals concentration of C, concentration of D over concentration of A, concentration of B. Since I got a constant over a constant, I'll just call it a new constant, which we refer to as a capital K. This ratio is important in the sense that it gives me the ratio of my products to my reactants to some constant K. As long as I'm at equilibrium, that ratio of products to reactants will always equal that K. Okay. Constant divided by a constant is just a new constant, so we call it capital K. This ratio is given a special name and symbol called the equilibrium constant K, relating to the equilibrium condition at a certain temperature. It's temperature dependent. That's important. Okay, this K is temperature dependent. So I know a K for a particular temperature. If I change the temperature, I got to change the K. So K is temperature dependent. So I know a reaction going on at a certain temperature. I have a K for that reaction. For a particular reaction relating concentration of each component. This is basically a comparison between the forward and the reverse reaction rates. At equilibrium, the ratio of concentration of species must satisfy K. So if I have equilibrium concentrations of C, D, A, and B, when I do put this into my equation, that ratio will be equal to that K value. If I don't have equilibrium concentrations, I'll just have initial values or any values, and I plug them into that, they will not equal K because they're not at equilibrium. Okay, only equilibrium concentrations, when I plug them into the equation, will equal to that K value. If I plug in any other values, they won't equal to that K value. Now, I can start reactions with reactants or just products or a combination of things, and eventually they reach equilibrium. Now, the concentrations of your C, your D, your A, and the B may vary from experiment to experiment. But when I'm at equilibrium, that ratio will equal K. So if I start off with just reactants, I'll come up with some concentration of CdAb at equilibrium. Ratio will be 7K. If I start off with just products, eventually I come up with different concentrations of CdAb, but that ratio will still be equal to that K value if we're at equilibrium. Every reversible system has its own position of equilibrium under any set of conditions. The ratio of products produced to unreacted reactants for any given reversible reaction remains constant under constant conditions of pressure and temperature. So if I'm at constant pressure and temperature, I'm at equilibrium, that reaction will exchange and continue exchange. Reactants will form products, products will form reactants, concentrations of all the species remain some constant value. However, if the system is disturbed, okay, the system will shift and all the concentration of the components will change until equilibrium is reestablished, which occurs when that ratio of new concentrations equal K. So if I have reactants and products and they add equilibrium, and then I add more reactants, then it's going to be unbalanced, and it's going to have to shift, in this case, toward the products, to form more products, consume that extra A, and then we're going to get different concentrations of A, B, C, and D. However, when it reaches that equilibrium, that ratio will still be equal to that K value. You got different concentration of different constant concentrations of your species, but the ratio will still be the same as before, equal to that K. Numeric value for this ratio is called the equilibrium constant, is given in reaction K, and remember that it is temperature dependent. It's temperature dependent. Okay, well, how do you write the equilibrium expression easily without having to do rate of your forward equal to your rate of your reverse and try to figure it out each time? Well, by this factor that we're going to talk about right now. The equilibrium constant expression for a reaction is obtained by multiplying the equilibrium concentrations or partial pressures of your products, dividing by the equilibrium concentrations or partial pressures of your reactants, and raising each component to the concentration to a power equal to the coefficient in the balanced chemical equation. So here's a generic equation. A, B, C, and D small letters are your coefficients. A, B, C, D capital letters are your species. So basically it's your products over your reactants, each raised to their coefficient. So you have your concentration of C to the little small c, which is the coefficient of C, time, concentration of D to the small d, which is your coefficient of D, divided by your concentration of A to the small a, time concentration of B to the small b. So in essence, we have products over reactants. Multiplied to their power, which is their coefficient. The brackets here indicate that you put molarity in here. So as long as you put in molarity into this expression for all your variables, and they don't have to cancel, they won't cancel, K is unitless. There are no units on K. Unitless as long as I plug in molarity. This is the same setup that we're going to do for all the equilibriums we talk for the next couple of chapters. If I talk about Ka or Kb, that's just telling me in an acid plus water or base plus water. We're still going to do it the same. Products over reactants, each raised to their coefficient. Another important thing to realize, liquids and solids have an activity of 1 because it's concentration based, We'll talk more about this later, but basically if a solid or liquid's in the expression, this chapter or in the chapters to come, they have a activity coefficient of 1. Therefore, they are not put into the expression. In the definition, we said that equilibrium concentrations are partial pressures, which means I can do this problem in gases as pressures as well. So it was set up the exact same way, except instead of doing it in molarities, we're doing it in atmospheres. So we're talking about partial pressure of C to the C, partial pressure of D to the D, partial pressure of A to the A, partial pressure of B to the B. Okay? As long as I plug in atmospheres here, it'd be unitless for my Kp as well. So I can do concentration based by doing aqueous solutions, or I can do gases, or I can do gases as atmospheres. Now we notice we have a subscript P on here. Since we do have that, sometimes instead of just calling it K, we would put a subscript C on it to mean concentration base. So you have a Kc and a Kp. As long as I'm putting in atmospheres, I have to use the Kp. If I'm plugging in molarities, I have to use the Kc. So the question comes up, is Kc and Kp the same value? And the answer is no. Okay, Kc is not the same as Kp. If I have atmospheres, I got to use the Kp value. If I have molarities, I have to use the Kc value, and Kc does not equal Kp. Now, it may be coincidental that it can be, so it is possible that Kc is equal to Kp, but most likely it won't be. And I'll show you later on when it can be equal, okay, and how you can tell if it would be the same value. But just keep in mind, if I'm doing atmospheres, gases as atmospheres, partial pressures, I want a Kp. If I'm doing gases or aqueous solutions as molarities, I want a Kc value. Other thing, as I said before, it is temperature dependent. Okay, so if I have a K, it's based on some temperature. Also realize if I do any changes by adding reactants, products, or whatever, that things are going to shift until it reaches equilibrium again. Okay, so all those concentrations will change. But in the end, when I reach equilibrium again and it's reestablished, that ratio will be equal to that K value. The law of mass action states that the value of the equilibrium constant expression K is constant for a particular reaction at a given temperature whenever equilibrium concentrations are submitted. So as long as I put equilibrium concentrations in my products and reactants, it will be equal to that K value. When that equilibrium concentration ratio equals K and concentrations are constant, so when I get to that point that my concentrations, my ratio equals that K, they will stay constant. Okay, those concentrations will stay the same value. However, if I disturb the system by adding something, removing it, whatever, those values will all change. All the concentrations of my reactants and products will change. However, when I reach that equilibrium again, okay, that ratio will be equal to that K value again. Equilibrium concentrations for reaction must be attained experimentally and then substituted into your expression in order to calculate Kc. So it has to be equilibrium values to plug in to solve for that Kc. In the early stages, we're going to be taking equilibrium concentrations and solving for K, but eventually I'll be giving you K, and then you're going to have to solve for the equilibrium concentrations, or how much is there when we actually reach equilibrium. Alright, consider the following reaction. What I want to show now, got carbon monoxide, hydrogen gas, gives me methane and water. What I want to show you is what I've told you a couple of times about, it doesn't matter if I start off reactants or start off with products. When this reaction reaches equilibrium, the ratio of its products to its reactants will equal some K. If I do the experiment again and start off with different concentration of reactants or products or mixture, when it reaches equilibrium again, even though I have different values of my concentrations of my products and reactants, it will still equal that K value. Let's start off this experiment with 0.1 molarity of carbon monoxide and 0.3 molarity of our hydrogen gas. Okay, so I'm starting off with those. That means I have no methane and no water. So am I at equilibrium? Well, the answer should be obviously no. I do not have a little bit of everything. I'll have reactants and I have no products, which means I'm not at equilibrium. So this reaction is going to have to shift one way or the other to establish equilibrium. So it means I'm going to have to consume up my reactants and produce some product. Well, knowing that, which way do you think this reaction is going to shift to reach that equilibrium? Yes, obviously it's going to have to shift to the right. I have no products, so this reaction is going to have to go to the right and form more products. In that process, what's going to happen is my reactants are going to decrease, okay, and my products are going to increase in concentration. Okay, as my reactants decrease and my products increase, my forward rate is going to be going down, my reaction rate of my reverse reaction will be going up, and eventually we reach that point of equilibrium. This is a very important concept to decide which way things go, because eventually I'm going to have to decide, do I put minuses on sides or pluses on sides to decide how to do my math. Okay, since this was going to the right, we know that these concentrations of my COs are going down, so I'm negatives, okay, and my concentrations of my methane and water are pluses, they're going up. As I said, important later on as we work problems. Now, eventually I'll give you the Kc value, and then you can calculate what the concentrations are going to be at equilibrium, but that's not my point right now. What I'm trying to do is show you that the ratio of your concentration of your products to reactants will be the same no matter how I start the reaction with reactants, products, or whatever. So let's just say, for argument's sake, I went to the laboratory and I experimented this experiment, and then after it got to equilibrium, I measured the concentration of all my species, was starting off with 0.1 molarity of CO and 0.1 molarity of H2. This is what I came up with. Okay, my CO concentration at equilibrium was 0.613 molarity. I measured the methane at equilibrium, and it was 0.0387 molarity. H2, 0.1839 molarity, and water was 0.0387 molarity. Notice these are the same value for methane as water because I got a 1-to-1 mole ratio. Not necessarily will they always be the same value. So I measured them. I got my concentrations at equilibrium. Now notice the numbers: 0.06, 0.03, 0.03, 0.18. Notice these when I do the next example and compare them. So that I know my concentrations, all I got to do is stick it into the equilibrium expression, and I can solve for my K. So how do you write your equilibrium expression? Well, you take your reaction, your products raised to their coefficients. So I have methane to the first power. I have water, okay, to the first power because they both got a coefficient of 1, divided by carbon monoxide, okay, and hydrogen gas to the third power, okay, because it's got a 3 coefficient. So I plug in the values. We said for methane it's 0.0387. For water was 0.0387. Carbon monoxide 0.0613. Hydrogen 0.1839. That's to the third power. Notice I don't have the units there because K is unitless. As long as I plug in molarities, I don't have to worry about units. It is unitless. I do the math, I get 3.93 as the K. So the ratio of products to reactants is 3.93. That is the K at this temperature for this reaction. Now make sure that you know how to do the math with expressions that go to the third power or the fourth power. So make sure you know how to use your calculator to be able to do this kind of math to get to your final answer. Now, the point I want to make with this, we just did the first one where I had reactants and it went to products, and we had some K, which is 3.93, and we had some concentration of species. Regardless if I start with initial concentration of reactants, or start off with initial concentration of products, or I start off with a little bit of everything, once equilibrium is established, the ratio of products to reactants will still be equal to that 3.93. So we're going to do the same experiment again, but I'm not going to start off with my reactants. I'm going to start off with products. So I'm going to take methane and water. And I'm going to start off with 0.2 molarity of methane and 0.2 molarity of water. Okay. Start this experiment exactly the same. Okay. Now notice I only have products and I have no reactants. Once again, is this at equilibrium? The answer is no. So this is going to have to shift one way or the other to establish that equilibrium. So if I do that, Okay, if I have no reactants and I have products, which way does this have to go? It's going to have to go to the left until I reach equilibrium again, which means basically the concentration of my methane is going to go down, my concentration of water is going to go down, concentration of hydrogen is going to go up, concentration of CO is going to go up until I reach that equilibrium, until I reach that point that my forward reaction equals my reverse reaction. Okay, my reverse reaction rate is going down while my forward reaction rate is going up till we reach that point of equilibrium, and then we reach some constant concentration of all our species. Once again, it's important to realize the shift, because when I do a problem like this, later on we'll be talking about calculations, we'll be talking negatives on this side and positives on this side because it's shifting to the left. I did the experiment again. I measured the concentrations, and I found CO to have a concentration of 0.0990, concentration of methane to be 0.110, hydrogen 0.2970, and H2O 0.110. Notice that none of these values are anything like the ones we did in the previous experiment. All these numbers are different. Okay, we had 0.03s, 0.18s, so all these numbers are different than what we had before. However, these are equilibrium concentrations, once again. So if I plug that into the equilibrium expression, when I do the math, it should be 3.93 again, since these are equilibrium concentrations. Once again, it's set up the same way. Products over reactants, methane to the first, water to the first, carbon monoxide to the first, and hydrogen to the third. Plug in my values for methane, 0.1010, water, 1010. Carbon monoxide, 0990, and hydrogen gas, 0.2970 to the third power. Put that into my calculator, and I get 3.93. Same value I had in the previous experiment. Notice the first one, I started with reactants, no products. This one, I started with products, no reactants. When they reached equilibrium, they all got some constant concentration value. That ratio still equaled 3.93. All of these are different values, but the ratio still equals 3.93 when it's at equilibrium. That's at equilibrium. Okay, when it's at equilibrium, the concentrations will be some constant value. Some constant value. So whether we start with reactants or products, at any initial concentration, the system establishes the same ratio at the same temperature. And remember, it's important, same temperature, that K value. All right, the equilibrium constant K is a value obtained for the equilibrium constant expression when equilibrium concentrations, not just any concentrations, are substituted. So it has to be equilibrium concentrations. That K also gives me some indication of which way things are shifting to reach equilibrium. At large K, K greater than 1, this is an indication that I have large concentration of products at equilibrium. Let's go back to your expression. You have K is equal to products over reactants. Well, for K to be greater than 1 and you have products divided by reactions, which one has to be bigger, your products or your reactants? Well, since products is in the numerator, this has to be larger, a larger value than reactants. So this is an indication that our equilibrium lies to the right, which means that since K is greater than 1, we expect this reaction to form a lot of products before it reaches equilibrium. Okay, it's form more products than it has reactions. Okay, lies to the right before equilibrium is reached. The opposite effect is happening if we're talking about K less than 1. Okay, this indicates a large concentration of unreacted reactants at equilibrium. Once again, look at the math. Products over reactants, if K is less than 1, that would mean that my reactants have to be larger than my products, which means it doesn't take much reactants before I reach equilibrium. Just a little bit has to react before I reach to that point where I reach equilibrium. So the equilibrium in this case lies to the left. So the size of your K can indicate where you're lying in your equilibrium. Okay, larger than K, forming a lot of products compared to reactants. Less than 1, forming a lot of reactants compared to products. Homework number 14. Ask you questions dealing with this information about equilibrium constants to see if you understand the concept. Now, you're going to do the same setup for all equilibrium equations for this chapter as well as the future. Okay, you're going to do products over reactants. The only difference going to be is that we're going to change a little subscript, okay, to tell you what it's about. Okay, where Ka is acid plus water, B is base plus water, Sp is solubility product, but it's products over reactants done exactly the same way that we're going to do all the things in here. So if you keep that in mind, that's going to make the other chapters a little easier for you as we go. Now, Kc is based on concentration, meaning molarity. Okay, you got to put molarity into Kc problems. And Kp is based on atmospheres. Okay, where atmosphere has to be placed into Kp problems. Okay, however, there's a difference between Kc and Kp. And to jump between these two, there's an equation. Okay, so what I want to do is talk about that equation, how to jump between one and the other. Now, for the most part in this chapter, if I give you molarities, I'm giving you Kc. If I give you atmospheres, I'm giving you Kp. Okay, so it's not a problem, but I do want you to understand that they are not equal and that you do have to do a change between Kp and Kc, and I want to give you that relationship before you can do it if you ever need to. Discussing gas phase equilibrium, it is often more convenient to express concentrations in terms of partial pressures rather than molarities. If I'm talking about gases and atmospheres, sometimes it's a little more convenient to deal with atmospheres to look at gases in terms of moles per liter. You can do it, okay, if you got a gas, you can talk in terms of concentration, moles per liter of solution. That's not a problem, but it just makes more sense to use atmospheres when we're dealing with gases. It can be seen from the ideal gas law, if you recall, PV is equal to nRT, that the partial pressure of a gas is proportional to the molarity. Okay, I'll take this V from my PV equals nRT and bring it down, which now gives me P is equal to N over V RT. Well, what's N over V? That's moles, and V is volume. That's molarity. So this is the same thing as saying P is equal to M RT. So you can see that P then is proportional to molarity, with a proportionality constant being RT. Remember, we talked about things are proportional. We can make them equal by putting some proportionality constant. So pressure is proportional to molarity with a proportionality constant of RT. So there must be some relationship between Kc and Kp, and there is, and we'll talk about that in a few seconds. So let's look at an expression. Carbon monoxide plus 3 hydrogen gases give me methane and plus water. I can work this problem 2 different ways. If I was given molarities, I could work this problem as a concentration base or a Kc problem. So basically I can write this in terms of my products over reactants would be my concentration of CO2, CH4 to the 1 times the concentration of H2O to the first divided by my carbon monoxide to the first times the H2 concentration to the third. Okay, so I can plug in molarities for each one of these and work this problem as a Kc. Or I may be given the atmospheres of things, given the partial pressures. So I can do the same thing, except it'd be partial pressure of methane times the partial pressure of water, both of those to the first power, divided by the partial pressure of carbon monoxide, divided by the partial pressure of hydrogen gas to the third power. Once again, I have to put in atmospheres for each one of these. Okay, as long as I plug in atmospheres, I work this as a Kp problem. So, if I'm given atmospheres, I just plug in things, do a Kp. If I'm given molarities, plug in my numbers, do a Kc. However, I can't do an atmospheres and plug it into a Kc, and I can't take a molarity and plug it into Kp. I can't do that. Okay, so if I'm given for some reason, I measure the partial pressures of something, but I can look into tables and only find the Kc of it, I'm going to have to do a conversion between Kc to Kp to work my problem. Kc is not equal to Kp. Now, it might be. There are occasions where Kc equals Kp, and I'll show you later where you can figure out where they would be the same value. But for the majority of the time, it's not, and you should assume they are not equal, okay, before using them. In general, you may need to jump between Ks. The numeric value of Kp differs from that of Kc based on the following. Kp is equal to Kc times RT to the delta Ng, where R is your ideal gas constant and T is in Kelvin. Okay, T has to be in Kelvin to cancel out with the ideal gas constant, which we're talking about, you may recall, 0.0821 liter atmospheres per mole Kelvin. Okay, you need kelvins there, that way they can cancel out. To the delta Ng. Okay, what is delta Ng? Delta Ng is equal to your number of moles of gas of your products minus your number of moles of gas of your reactants. Okay, key word there is gaseous. Okay, it's my number of moles of gaseous product minus my number of moles of gaseous reactants, which means if I have liquid, aqueous, those are not accounted for. Okay, you do not account for those. We're only looking at gases. We're talking about atmospheres, partial pressures. Those are not affecting partial pressure. So your RT is raised to that delta Ng power. So let's look at an example. So I got sulfur dioxide plus oxygen gives me sulfur trioxide. Okay, I know the Kc for this reaction is 280 at 1000 Kelvin. Calculate the Kp for this reaction at this temperature. Now, let's say for some reason they gave me atmospheres, and I measured it, gases as atmospheres, and I looked in tables, and all I found was Kc was 280. Well, then I want to do this as a Kp problem because I know I only have atmospheres, so I need to convert that Kc to Kp before I can work my problem. So I need to plug that into my equation to convert it from Kc to Kp. So Kp is equal to Kc times concentration of RT, and that is RT is raised to the delta Ng power. So I have to figure out my delta Ng. Well, I have to take my number of moles of gaseous product, which in this case is, I have 2 moles of SO3, so that's 2 moles, minus my moles of my reactants. I have 2 moles of SO2 gas and 1 mole of O2 gas. That's a total of 3 moles, which gets me a -1 as my delta Ng. That is my power that I would be raising my RT to. Now, realize that is gaseous, okay, only your gases. Okay, say for argument's sake I had here another H2O liquid. Okay, would I account for that 1 mole and call this 3 moles? And the answer is no, because that's a liquid, so that wouldn't be part of it. Okay, only gaseous, only your gases do you account for the number of moles. Now remember I said that sometimes Kp will equal Kc. When would that occur? Well, hopefully now you can figure out when that would occur. When is there a case where Kc would equal Kp? That would be a case where my delta Ng is 0, because anything to the 0 power is 1. So this occurs when my number of moles of my gases equals my number of moles of my number of moles of my gas products equals my number of moles of my reactant gases, then Kp will equal Kc. So in those situations, it is possible that Kp will equal Kc if my number of moles of gas products equals my number of moles of reactants. Other than that, there should be different values. So continuing on with this problem, okay, we will go ahead and plug in our Kc, our R and T, and delta Ng. So for Kp, we plug in, Kc, we plug in 280. We plug in R, which is 0.0821 liter atmosphere per mole Kelvin. We plug in our temperature, which is 1000 Kelvin. Remember, that has to be the same units for I can cancel. So if I'm given to me in Celsius, I'm going to convert it. And all that raised to the -1 power, which we calculated as our delta Ng. Recall that it is this whole expression that goes to that -1 power. So it's 0.0821 times 1,000. That is to the -1. Make sure you know how to use your calculator to make that happen. Time my 280, which then gets me my Kp to be 3.4. Notice Kc and Kp are totally different numeric numbers. Okay, so that would be the number that I would use for my Kp, and then plug in my atmospheres and move on with my problem.